Hello there, welcome back to the Differential Equations by Alexander. Okay, so today what I want to talk about is on exact equations, but I want to give you examples. On the previous video we said what are the exact equations, and so today I want to give examples on how to solve them. But before we do that, let me just review what we did last time briefly. So we did a little bit of calculus 3 last time. So we had the function f, and then we assumed that the function is a function of two variables. And if that is the case, then you can differentiate the function with respect to the x variable, and then you can also differentiate with respect to the y variable. Okay, so now each one of those red box form functions are functions, so that means that you can differentiate them also. So you can differentiate with respect to the x variable and then with respect to the y variable, and then same thing for the other guy. So you can differentiate with respect to the x variable and also differentiate with respect to the y variable. All right, so now one of the things that we need to know from calculus 3 is that if the second derivatives are continuous, then there's a theorem called Chlarospheron that says that those two things are equal to each other. Okay, so those two things are equal to each other, and that actually is the important part that we need to use for us to solve the differential equation. So right now this is just calculus 3, but just keep this picture in mind. You start with the function f, and then you have this second layer, and then you have this third layer, and we kind of look at the third layer to figure out some information about the first layer. All right, so I'll give you the details later. But now what I want to say is the method that we talked about last time was the following. We have 3 steps. So we want to verify exactness, okay? And so the type of differential equation that you're looking at is something that looks like this. So m of some function m multiplied by the dx plus some function n multiplied by the dy is equal to 0. And so to verify the exactness, and what that means is that we want to know, is there a function f, okay? Is there a function f that will give us the function m and then the function n, okay? So what we need to do to verify exactness is very simple. We are going to calculate the following information. We're going to differentiate the function m with respect to the y variable, and then we're going to differentiate the n function with respect to the x variable. Notice that in the equation, the m is next to the dx and the n is next to the dy. Okay, so just make sure you pay attention to that. But to verify exactness, we calculate these derivatives, and what we want to check is we want to know whether these are equal to each other. Okay, that's what we need to do. And if they are equal to each other, then we do say that the equation is an exact. So if equal, then the equation is exact. Let's just write down ODE is exact. Okay. And so what does that mean? That means that there is a function f from the very beginning that can help us get the m function and then the n function, and that's going to help us figure out the solution to the differential equation. So the first step is to check that it is exact. The second step is how do you figure out the f function from the information that's given to us. Okay, so what I'm going to do is the following. So here's the f function, and then what we know is the m function and then the n function from our differential equation in differential form. And so the way that I think about it is the following. So I'm going to follow 2 steps. So 3 steps technically. So this is going to be my first step, my step A. I'm going to use the m function to get the f function. Then I'm going to use that. There's a catch there. And so I need to kind of actually go down 1 step. So let's call that the B step. So go down to the n function, and then I'm going to go up, and that's going to be my step C. So I'll explain that in more detail afterwards, but just know that actually I'll say what the A, B, and C steps are here. And so step A means the following. The f function, all you have to do is you have to integrate the m function with respect to the x variable. But there's a catch. The catch is that there's going to be a constant. In this case, there's going to be a constant that depends on the y function. So you kind of have your formula for the f function, but you don't know what the c function is. So that's why you go into step B. You're going to differentiate this formula that you just got, but you're going to differentiate this with respect to the y variable, and then you're going to make it equal to the n function. So that's how you use the other n function. So now you try to solve for the c or y function, and now step C is essentially updating your function f. So you have your function f, which you already had the formula from the first step, and then you update your formula for the C part. Okay, so that's roughly the idea here. But I'm going to go into this examples just to show what this is, what this looks like. All right, so now that suppose that you have a formula for your f function, so suppose you have a formula, and now the solution to the differential equation that was given to you in the very beginning, and remember the differential equation was something like this. So the solution to the differential equation is going to be the following. All you have to do is you make the function that you just found, you make it equal to c. Okay? You literally just make it equal to c, and then solve for y if possible. Okay. So this is a very tricky part here, if possible. Not always is it possible, but for the majority of our problems, it will be. All right, so let's go into the example just to see how this looks like. And again, just to give you the idea again, so step A was to integrate the m function. Step B was to differentiate the function formula that you have for f, and then make it equal to the n, and then you solve for c, and then you update your formula for f. That was step C. So that's the little picture that I have in mind, just to kind of organize my thoughts. All right, so let's start with the first example. So we have a differential equation, and we want to check that this is an exact differential equation. And so what we need to do is we need to identify the m. So this guy in the blue box, that is going to be my m. And then this guy in the other blue circle, that's going to be my n. So to verify exactness, all we have to do is we want to differentiate the m, but we need to differentiate this with respect to the y variable. So differentiate with respect to the y, then you get this to be equal to 2x. Now you look at your n formula, and then you are going to differentiate this with respect to the x variable. And so the derivative with respect to the x variable is equal to 2x. And what do you notice about those two things? And so you calculate those two things separately, and now you have to ask yourself, are those two things equal to each other? And then the answer is yes. Okay, so if the answer is yes, then the ODE is exact. Okay, so that's how you check the exactness of a differential equation. Okay. All right, so now we're going to go into step number 2. So step number 2 says to find the formula for f. Okay, so exact means that you have the m and you have the n, and then now you want to basically find the f formula that if you were to differentiate with respect to the x variable, this will be the m. And if you were to differentiate the f function with respect to the y variable, this will be equal to the n. So that's what that means, okay? So that's what exact means, that there is some function f that gives you the m and the n. All right, so let me just erase this, and let's start trying to figure out what the formula for the f function is. Okay? We need to find the f. So step A is going to be integrate the function m, but we're going to integrate this with respect to the x variable. And so here I put in my 2xy, and then integrate with respect to the x variable. And if you do integrate this with respect to the x variable, you'll get x squared y, and then technically there's a plus c here, but this c is going to be a function of the variable y. That is one of the tricky parts that we have to think about here, because this is a little bit of Cal 3 now. So we integrate, and then we do get this constant c, but this constant is going to be a function that depends on the variable y. So that what that means is that you now have your formula for f, except that you don't know what the c function is. Okay? You don't know what the c function is. And so that is the goal for part B. Part B is us trying to figure out what the c formula is. So what we do is we want to differentiate the function f with respect to the y variable, and then we're going to make it equal to the n. So that's what we are going to do. So this is step B. And so differentiate the function f with respect to the y variable, then this is going to be x squared plus c prime of y. This is going to be made equal to the n formula. So this is x squared minus 1. So notice that this is just using step number B. All right, so now we need to figure out the c. Okay, so the x squares can go away, and so c prime of y is equal to -1. But this is the derivative of c. What we care about is what is the c function. So the c function will be equal to -y. Okay, the c function will be equal to -y. And technically, yes, there is a extra constant here at the very end, but at this point, we're not going to write it down. So what does that mean? Okay. So we have one more step to go. So this is step C. And then what that means is that we're going to update our formula that we had from step A. And now we're going to update the formula. And now our formula is going to look like this. So we have x squared y and then minus y. Okay, so that's updating the formula, and that is step C. And again, I want to remind you of the picture that we had. So we have the F, we have the M, and then the N. Step A was getting the formula for F, but we did not know that C part of the formula. And so we need to go to step B to figure out the C formula. And then step C basically was just updating the formula F. All right, so we have a formula for the F now. Okay, so that is step 2 for solving the differential question. And so now we can go to step number 3. So I wrote down the formula again here that we just found for the F formula. And step number 3 is probably the easiest one. Okay, so this one just says you make the function that you just found, you make it equal to a constant C. So all you have to do is you make the formula that you just got, the formula, you make it equal to a constant C, and if you can solve for y, you solve for y. So in here we are going to factor out, so x squared minus 1, y is equal to c. And so what that tells us is the following. We get the y is equal to c divided by x squared minus 1. And that is the solution to the differential equation. Okay? So remember, this is the differential equation that we want to solve. And we're trying to figure out what is the function y that satisfies this differential equation. We changed the problem into a little bit of calculus, and now we have a formula for the y. So y is this function, c divided by x squared minus 1, and this satisfies the differential equation. All right, so that's one example. And now I'm going to repeat the process again for 2 more examples. So if you're okay with this, then this is all you have to look at. But let me just give you 2 more examples showing the same steps. All right, so the differential equation is not given to us in differential form, but we still want to show that this is an exact differential equation. So what that means is that we need to put this into an exact form. And so what that means is that we need to move this to this side and then move this to the other side. And so kind of like cross multiply. And so if you do that, and then you do a little bit more algebra, so you get the following. So y squared minus cosine x sine of x. This is multiplied by the dx. And now what I'm going to do is this is going to be minus y, 1 minus x squared dy is equal to 0. Okay, so do a little bit of algebra, and then this is your differential equation in differential form. All right, so now I put this into this format because I want to identify my m and my n formula. So this guy is going to be my m function, and then this guy, included the negative sign, that is going to be my n formula. And I'm going to rewrite the n formula with the distributing the negative, so negative y minus yx squared. Okay, we're going to need that later on. All right, so now that we have identified the m and the n, now we do the verifying the exactness. So how do you verify the exactness? So what we have to do is we are going to differentiate the m formula, but we're going to differentiate this with respect to the y variable. So differentiate with respect to the y variable, this formula, what do you get? Then we get 2xy, that's it. All right, so that's the derivative of m with respect to the y variable. Now let's look at the n function, and now we're going to differentiate the n function with respect to the x variable, and differentiate with respect to the x variable, what do we get? And one little correction here, this is supposed to be a plus right here, so plus. And so the n function, differentiate that with respect to the x variable, that is going to be a 2yx, which is the same thing as the other one. Okay, so now these are equal to each other, so this is a check mark there. And if we do say that these are equal to each other, then we are saying that yes, that this differential equation is an exact. So ODE is exact. And what does that mean? It means that there is a function f. There is a function f on the very top that is going to give us the m and then the n. So m and n. And we are supposed to figure out the function f in the next step. So I rewrote my differential equation in differential form. That way it's easy to work with. And now we need to find the formula for the f. And so we need to do the reverse engineering, okay? And so what is step A? So step A, and let me write this in blue just to change the colors. So step A says that your formula for the f function is just going to be simply integrate the m function with respect to the x variable. And so this is going to be xy squared minus cosine x sine x dx. So now how do you integrate this guy? Okay, so this is going to be 1/2 x squared y squared. And for this guy, for the second term, you have to use a u substitution or change of variables, if you want to call that. And you'll end up with the following. Okay. So this is going to be a 1/2. Yeah, it's going to be a plus 1/2 cosine square of x. Okay, so that the integral of that underlined blue stuff is going to be plus 1/2 cosine square of x. And then you are going to put in a function that depends on the variable y. So this is a constant, but it's a function that depends on the variable y. And so now this is your formula for f. Okay, so you have found your formula for f, except that at this moment we do not know the formula for the extra constant function. All right, so that means that we have to go into step number b. Okay, step b says that we want to differentiate the function f, and we're going to differentiate with respect to the y variable, and then we're going to make it equal to the n formula. Okay, so the function that we just got, we're going to differentiate this with respect to the y variable, and then what is the derivative of this with respect to the y variable? So this will give us x squared y, the second term goes away, and then plus c prime of y is equal to the n function. So we're going to make this equal to the n function, and then that turned out to be a negative y plus x squared y. Okay, so that's our n function here. That's the n function on the very top. So we can cancel out the x squared y, and so that means that the c prime of y is equal to negative y. And what that means is that the c function, so c of y is equal to negative 1/2 y squared. Negative 1/2 y squared. So what does that mean for our problem? Okay, so for our problem, remember that we already had the formula for the f, but we did not know this extra c at the very end. And so what we need to do is we need to update the c function. Okay, and that's going to be our formula for the f. Okay, so step c says to update the formula for c. So when we do that, I'm going to type up the solution here for you, and so this is what we get. So this is the function that we get, okay, after we finish step number 2. We find the formula for f. Now step 3 is the easiest one, and so all you have to do is you make the formula you just got, you make it equal to a constant c. And so if you do that, then we have 1/2 x squared y squared plus 1/2 cosine squared x minus 1/2 y squared, and then we make the whole thing equal to a constant c. And if we can, we want to solve for y here. Okay, so let's see what we could do. So first of all, we can eliminate all the 1/2 in here. So eliminate all the 1/2s. You can cancel it out. Technically, you multiply by 2, but then if c is a number that you don't know, then 2c is still a number that you don't know. So we still just write down c here, okay? So that's one thing we could do. And then the other thing we could do is we can factor out the y squared. So that will be x squared minus 1 y squared. And then this will be c minus the cosine square of x. I'm doing a little bit of algebra here. And then we'll get to y squared is equal to c minus cosine square of x divided by x squared minus 1. Okay, so I will stop here. Otherwise, we'll have to consider more conditions in this. But at this point, you were technically done with the problem. Actually, you were done with the problem in the very beginning when you made the whole function equal to 0, equal to the constant c. So that's all you do. And in some problems, like I told you in the beginning, in some problems you are not able to solve completely for the y variable, the y function. So your solution is going to be an implicit solution. All right. So let me just go let's go to the next example, and that will be the last example for today. And so what I want to do in this example is a little bit different. So I gave you a formula before that if you have your m and your n, then to find for step number 2, so not the step 1, but step 2, then I told you before that you start with the m and then you use the other information. But you can actually start the process the other way around. You can start with the n function, and then you use the m function on step B, and then you update your formula for C. And what that means is the following. That means that you integrate the function n, but you have to integrate with respect to the y variable, and that's going to be your formula for the f, okay? But there's going to be a constant c, okay? There's a constant c that you don't know, and so this part B says to differentiate the function f, but you're going to differentiate this with respect to the x variable, and then you're going to make it equal to the m function. And then step C is update the f. Okay, so that's the steps. Those are the steps that we're going to follow on part 2. All right, so let me just clear this up, and then before we start trying to find the f function, we need to figure out whether this is an exact differential equation. Because if it is not exact, then this whole process about the reverse engineering the f function doesn't work. Okay, we will be stuck in the limbo. All right, so we identify the m function to be that guy, and then we identify the n function to be that guy. So to verify exactness, we want to differentiate this with respect to the y variable. And so the derivative of this first function m, differentiate this with respect to the y variable, then you get 4x. Okay. Now differentiate the n formula, differentiate that with respect to the x variable. So the derivative of this with respect to the x variable, then you get 4x also. And so now we see that these two guys are equal to each other. And so we can say that the ODE is exact. And so what that means is that we now can go and find the f function. Okay, so that step 1 is check that this is an exact differential equation. And if this is an exact differential equation, then that means that we can go and try to find the function f. Okay, and now this is we switch gears a little bit here, and we are now going to do a little bit reverse engineering. And so what I'm going to do here, step A, I'm going to write it out a little bit different here. So this is going to be integrating the n function with respect to the y variable. Okay, so let me just draw the picture here. So f m n, and so step A is going to be use the n to figure out the f. Okay, so if you plug in the n formula here, you get 2x squared plus 2y, and we are going to integrate this with respect to the y variable. And if you do integrate this with respect to the y, then you get 2x squared y plus y squared plus c. But that c is a function that depends on the variable x. So let me just rewrite it here a little bit more clear. What we got is 2x squared y plus y squared plus a constant, but that constant is a function that depends on the x variable. Make sure that you now know that this is a constant, a function that depends on the x variable. And so here is your formula for the f, but now we need to figure out what the formula for the c function is. And so that's where we go into step B. So step B is basically to find that c function. And so what we need to do is we're going to differentiate the function f, and then we're going to differentiate this with respect to the x variable this time. And now we're going to make this equal to the m. And so I'm switching gears a little bit just to show you that there's a second way to solve this, and there is also a third way, but that's a different story. All right, so now differentiate the function f with respect to the x variable, then we'll get 4xy. We differentiate with respect to the x variable, the second term goes away, and then the last term is a c prime of x. And now we're going to make this equal to the m. Okay, and then the m turned out to be 3x squared plus 4xy. Okay, and so what does that mean? Okay, so that means that we can cancel out the 4xy from this equation, and so now we integrate this guy, and then the integral of the c function is 3x to the third divided by 3, and so this just simplifies to x to the 3. And then yes, technically there is a constant there. And so now what do you do with this thing? Okay, so step C is you update your formula. You already had your formula for the f here, but you did not know what the c function was. And so now you can update the formula. And so this is going to be 2x squared y plus y squared plus x to the third. Okay, so that's our formula. And now what I want to do is, so we're done with the hard part now, and then what we need to do is to solve the differential equation, we make the function formula that we just found, we make it equal to the constant c. So I rewrote the function here, And so all we have to do is we make this equal, this formula, we make it equal to the constant c. Okay, and now if we can, we try to solve for the y. Otherwise, we are done here, and then this will be an implicit differential solution. All right, so I'll stop here, but I'll let you think about whether it's possible to solve for y here, and I'll give you a little hint. This is a quadratic in the y variable. And so now that you have this, you're done with the problem. The original problem was a differential equation, but we did a little bit of calculus to reverse engineer the function f, and then from there we find our solution. All right, so that's all. That's all I have for today. I hope that 3 examples repeating the process of the 3 steps and with a diagram, I hope that that is helpful, and I'll see you next time. Thank you for watching.